Okay, so next we're going to look at a series of examples that takes us in the direction of the quaternion group. So let I sub 2 be the 2 by 2 identity matrix, and let the matrix sigma be the matrix with entries 0, 1, negative 1, 0. Determine the order of and construct the Cayley table for the smallest group under multiplication that contains the matrices, the identity matrix and the matrix sigma, and verify the group structure by definition. Okay, so in order to have a group, we must first have a magma, so we need closure under the operation of multiplication of the elements. Now, identity times identity is identity, and identity times sigma in any combination or in any order is sigma. And so now we calculate the product, sigma times sigma. And this is the 2 by 2 matrix with entries 0 plus negative 1, 0 plus 0, 0 plus 0, negative 1 plus 0, and this is the negative identity matrix. So notice that with this product, all that we have done is to introduce a scalar multiple, by the scalar negative 1. And so we must also have negative sigma. And so let the set G be the set which contains plus or minus the identity matrix and plus or minus the matrix sigma. We now have enough to construct the Cayley table. Now this time we will construct the actual Cayley table without the superfluous information. So we have as the first row identity, sigma, negative identity, negative sigma, and also as the first column identity, sigma, negative identity, and negative sigma. Now sigma times sigma is negative identity, sigma times negative identity is negative sigma, and sigma times negative sigma is identity. Now, negative identity times negative identity is positive identity, and negative identity times negative sigma is positive sigma, and negative sigma times negative sigma is negative identity. So notice from the Cayley table that we do indeed have closure of the elements under multiplication. The set does contain an identity element, and each element has an inverse. Further notice that this table, the Cayley table for this structure, is identical to the Cayley table for the integers modulo 4 under addition, and so this is indeed a group. It is, in fact, a group isomorphic to the integers modulo 4 under addition. But in the example, or by the instructions of the example, we need to verify group structure by definition. So let's do that. So as the set G is closed under multiplication. The set together with the operation of multiplication is a magma. Now, if we were to verify associativity by direct computation, we would need to perform 4 cubed, or 2 to the 6th power, which is 64 computations. Now, fortunately for us, we have already demonstrated that matrix multiplication is associative way back in lecture 4. So as matrix multiplication is associative, the set G under multiplication is a semigroup. Now there exists the 2x2 identity matrix, which is the identity for this group. So there exists this element such that for every matrix A in the set G, we have that A times identity is the same as identity times A, which is A. And so the set G under multiplication is a monoid. And for every matrix A in the set G, there exists an inverse matrix, an inverse for that matrix also in the set G, such that A times A inverse is the same as A inverse times A, which is the identity. And namely, the inverse of the matrix A is the matrix A if A is plus or minus the identity matrix, and is negative A if A is plus or minus the matrix sigma. And so the set G together with multiplication is a finite group of order 4. Further, as the Cayley table for this group is identical to the Cayley table for the group consisting of the integers modulo 4 under addition, we have that the integers modulo 4 is isomorphic to the group G under multiplication. So as the next example, we will show via an explicit isomorphism that the integers modulo 4 under addition is isomorphic to the set G under multiplication. So let phi be a map from the integers modulo 4 into the set G, and let this map be defined by phi of 0 is the identity matrix, phi of 1 is the matrix sigma, phi of 2 is negative identity matrix, and phi of 3 is negative sigma. So let's add this to our table. Phi of 0 is the identity, phi of 1 is sigma, phi of 2 is negative identity, and phi of 3 is negative sigma. So clearly, the map phi is a bijection. We now need to show that this function phi is a homomorphism. Phi of the sum, 0 plus 0, is the same as phi of 1 plus 3, which is the same as phi of 3 plus 1, which is the same as phi of 2 plus 2, all of which is the same as phi of 0, which is the identity matrix. Now phi of 0 times phi of 0 is identity times identity, which is identity. Phi of 1 times phi of 3 is the same as phi of 3 times phi of 1. And this is negative sigma times sigma, which is identity. And phi of 2 times phi of 2 is negative identity times negative identity, which is positive identity. Now phi of 0 plus 1 is the same as phi of 1 plus 0, which is the same as phi of 2 plus 3, which is the same as phi of 3 plus 2, all of which is the same as phi of 1, and phi of 1 is the matrix sigma. Now phi of 0 times phi of 1 is the same as phi of 1 times phi of 0, which is sigma times identity, which is sigma. Phi of 2 times phi of 3 is the same as phi of 3 times phi of 2, and this is negative sigma times negative identity, which is positive sigma. Now phi of 0 plus 2 is the same as phi of 2 plus 0, which is the same as phi of 1 plus 1, and this is the same as phi of 3 plus 3, all of which is the same as phi of 2, and phi of 2 is negative identity. Now phi of 0 times phi of 2 is the same as phi of 2 times phi of 0, and this is negative identity times identity, which is negative identity. Phi of 1 times phi of 1 is sigma times sigma, which is negative identity. Phi of 3 times phi of 3 is negative sigma times negative sigma, which is negative identity. Now phi of 0 plus 3 is the same as phi of 3 plus 0, and this is the same as phi of 1 plus 2, which is the same as phi of 2 plus 1, all of which is the same as phi of 3, and phi of 3 is negative sigma. Phi of 0 times phi of 3 is the same as phi of 3 times phi of 0, which is negative sigma times identity, which is negative sigma. phi of 1 times, and this is negative identity, times sigma, which is negative sigma.
And so for every pair of elements, A and B, in the set of integers modulo 4, we have that phi of A plus B is phi of A times phi of B, and hence the map phi is a homomorphism. And thus the map phi, which is a map from the integers modulo 4 into the set G, is an isomorphism. And therefore, the integers modulo 4 is isomorphic to the set G under multiplication. So let the set M be the set which contains plus or minus I, plus or minus M sub 1, plus or minus M sub 2, and plus or minus M sub 3, where I is the matrix with entries I sub 2, 0, 0, I sub 2. M sub 1 is the matrix with entries sigma 0, 0, negative sigma. M sub 2 is the matrix with entries 0, I sub 2, negative I sub 2, 0. And M sub 4, M sub 3 is the matrix with entries 0, sigma, sigma, 0. Now notice that these matrices are actually 4 by 4 matrices, but we can treat them as 2 by 2 matrices, and this will make the computation easier. Notice that the elements in, or the entries in these matrices, are exactly those elements that we just worked with in the previous example. And so we know what the product of any of these entries are. So we are going to construct the Cayley table for the set M under multiplication and verify the group structure by definition. Now, the products with the identity matrix are obvious, and also the scalar multiples, where the scalar is -1, those are also obvious, but this still leaves us with 9 products to compute. And so I have done some prep work. So let's start computing. M1 times M1 is the matrix with entries sigma squared plus 0, which is negative I sub 2, 0 plus 0, 0 plus 0, and negative sigma times negative sigma, which is negative I sub 2, and this is negative I. M sub 1 times M sub 2 is the matrix with entries 0 plus 0, sigma plus 0, 0 plus sigma, 0 plus 0, and this is the matrix M3, M sub 3. M sub 1 times M sub 3 is the matrix with entries 0 plus 0, sigma squared plus 0, so negative I squared, 0 plus negative
sigma times sigma, which is I sub 2, and 0 plus 0. Notice that this is the negative of the matrix M sub 2. M sub 2 times M sub 1 is the matrix with entries 0 plus 0, 0 plus negative sigma plus 0, and 0 plus 0. Notice that this is the negative of the matrix M sub 3. M sub 2 times M sub 2 is the matrix with entries 0 plus negative I sub 2, 0 plus 0, 0 plus 0, negative I sub 2 plus 0, and this is negative I. M sub 2 times M sub 3 is the matrix with entries 0 plus sigma, 0 plus 0, 0 plus 0, and negative sigma plus 0. Notice that this is the matrix M sub 1. M sub 3 times M sub 1 is the matrix with entries 0 plus 0, 0 plus negative sigma times sigma, which is I sub 2, 0 plus 0, oops, sigma times sigma plus 0, which is negative I sub 2, 0 plus 0, which is 0. And so this is the matrix M sub 2. M sub 3 times M sub 2 is the matrix with entries 0 plus negative sigma, 0 plus 0, 0 plus 0, and sigma plus 0. Notice that this is the negative of the matrix M sub 1. And finally, we have the matrix M sub 3 times M sub 3, which is the matrix with entries 0 plus sigma squared, which is negative I sub 2, 0 plus 0, 0 plus 0, sigma squared plus 0, which is negative I sub 2, and this is negative I. So we now have enough to construct the Cayley table.